it on Google platform or to have it in Zoom or how to have it. She consulted everybody and she has achieved it, and the whole department has achieved it. They deserve to be congratulated for this special preparation. And all those who have participated or willing to participate in this 2 days conference, which will be very relevant from the guidance from the head of the department. I heard about the topic, how current it is, how relevant it is, especially the materials that they are going to use, whether it is crystal or it is nanomaterials or whatever be the materials which you are going to use currently has a relevance, because the medical field is struggling to overcome this COVID. How to prepare a vaccine, what to do, the whole world is suffering. Anyway, they have chosen a relevant topic, and all the experts, the resource persons, starting from Dr. Srinivasan, who is a friend of ours and who is a guiding force, I could say, who has guided Radhika to have this title, and which will be really relevant to all of us, to even the common man. I'm not a physicist, or the principal is not a physicist, and all the laymen who are going to listen to this conference, because it is going to be placed on YouTube, which will be very, very useful. How physics is useful. Physics is a lovely subject, and it has relevance. It is useful for the to solve the day-to-day problems of mankind, and especially these materials in the medical field. I've heard about the crystals used in the medical field. I've heard about the nanomaterials, how this, for example, even I'm a cancer survivor. I know how people are finding it difficult to give treatment for this cancer disease. But now, when they give a treatment, it affects the whole body. When you go for chemotherapy, it affects all your cells, and it kills all the good cells of your body also. See, recovery seems to be very, very difficult in the case of cancer. So what I have read in a newspaper article is, from that I'm talking about, I'm not a physicist, again I'm stressing that point. See that they say this nanomaterial is going to just take up that particular part and try to treat that particular cell which is affected, which will be a greatest discovery. I don't know whether it is applied, it has been applied already. If it is applied, number of people will be using that, and the cancer is a dreadful disease which is spreading all over the world, and the forecast says many more will be affected because of the kind of the food that we are eating and the pollution which is existing in the society. So whether it is a crystal or whatever material you're going to study this conference, and the deliberations that you're going to make, and the presentations of the scholars, and the resourceful persons talks are going to be useful not only to the physics students, it will be useful to the whole society. I'm sure it will be a successful one. I wish you all the best, especially the organizers and the physics department and the students of physics department and the resource persons who have accepted to contribute towards this conference in spite of the fact that it is online. And I'm happy. I want to congratulate all of you, and I'm thankful to all the organizers and the resource persons and the participants. All the best once again. Thank you for this opportunity. Thank you. Thank you, Radhika.
Thank you, ma'am. Thank you.
Thank you, ma'am. Thank you for your constant encouragement and support. You don't have to be great to start, but you have to start to be great. Here comes our staff member, Mrs. T.N. Priyadarshini, Assistant Professor, Department of Physics, to introduce the speaker of the session.
Good morning, everyone. I extend a warm welcome to all. I find immense pleasure in introducing our Honorable Chief Guest, Dr. Srinivasan, Professor and Head, Department of Physics, School of Physical Sciences, Bhatia University, Coimbatore. Sir has completed his bachelor degree in Government Arts College, Salem, master degree in National College, Trichy. He did his PhD from Alagappa University. Sir has acquired postdoctoral research fellow at Department of Pure and Applied Chemistry, University of Strathclyde, Glasgow, United Kingdom. He has received CSIR Senior Research Fellow Award in 1994, International Union of Crystallography Young Scientist Award in 1998, Government of Tamil Nadu Best Book Award in 2001, Japan Young Scientist Award from International Union of Crystallography ISSC G11 and International Organization for Crystal Growth ICCG 13. Certificate of Achievement Award from Alagappa University in 2006, DST Serb Young Scientist Award in 2007, INSA Travel Grant Award in 2013, Arivial Kalanyam Best Scientist Award from MTS Academy in 2016. IACG Professor P. Ramaswamy National Award for Crystal Growth and Characterization in 2018. He is a life member in Indian Association of Crystal Growth, Materials Research Society of India, Indian Laser Association, Indian Physical Society, and Indian Science Congress Association. Annual member in British Association for Crystal Growth, Optical Society of America, and American Chemical Society. He is a member in Editorial Advisory Board, Crystal Research and Technology. He has received more than 1 crore from various funding agencies of Government of India, such as Council of Scientific and Industrial Research, DRDO, BU-CLS, UGC MRP, DST, SCRC. He has produced 8 PhD scholars, 49 MPhil scholars, and 61 MSc students. He has published more than 70 research articles in reputed international journals. Sir has presented more than 50 research articles in international conference and nearly 100 research articles in national conference. The number of citations for his research articles on 11/10/2010 are around 953. H index is 18 and I index is 29. A cordial welcome to you, sir. We are honored by your presence, sir. Thank you.
Thank you, ma'am.
Thank you, ma'am. Thank you for the brief introduction. I am profusely elated to take an opportunity to invite our chief speaker of the session, Dr. K. Srinivasan, sir, Professor and Head Department of Physics, Bharatiya University, Coimbatore, to take over the session. Session is over to you, sir.
Thank you. Thank you, ma'am.
Sir, warm welcome to you. This is Jagda Lakshmanan. It's great, lovely that you accepted our invitation. We are so happy to have you for this conference. This is the first conference that the physics department is organizing. And I'm sure in spite of this situation, the whole year will be a successful year because they are inaugurating the conference with you. And I'm happy that you have accepted it. Thank you, sir. Thank you.
With your
Thank
blessings,
you.
madam. With your blessings.
Thank you.
Most esteemed Professor Jagda Lakshmanan, the Chief Executive Officer of the institution, esteemed Principal Dr. Maithili ma'am, respected Dr. Radhika, the Head of the Department of Physics, P.K.R. Arts and Science College, my dear colleagues and faculty members from the college, students of the department, and various participants from various institutions to this 2 days national event on advanced functional materials being organized by one of the most prestigious institutions affiliated to Bharatiya University. Good morning, everyone, and I feel very, very happy and privileged to take part in this inaugural function of this 2 days event. And I have a great opportunity to deliver a lecture on our own research field in this August forum. Dear friends, as Professor Jagda Lakshmanan Madam rightly pointed out, we are in need of several of the materials for our day-to-day applications, especially in medical field. It's a need of the hour. The entire world is facing a crisis, a pandemic. So looking forward, at least one medicine to resolve the entire problem. This is not the problem of one man or one country. The entire globe is facing. So this situation itself very clearly infers to all of us that how the materials play a major role in our day-to-day life. Friends, we are living in a materials world. Everywhere there are materials. In the field of science and technology, there are different kinds of materials are being used by exploiting their important properties. Materials right from the semiconducting materials rules the entire electronic world, right from the diode to a large scale integrated circuits. The entire solar industry, silicon, it's a key material. The entire laser industry depends on the laser crystals, right from ruby to India, glass, etc., etc. And medicinal field, there are n number of drug materials, pharmaceutical materials. So they are being augmented every day and produced in larger quantity to meet our needs. And similarly, several of the biological materials, proteins, and various other technological materials, strategically important materials, irrespective of their nature, whether they are organic or inorganic or semi-organic, irrespective of their size, right from the nano, as Madam rightly pointed out, up to a meter by meter single crystals used for laser fusion applications. So here the physics, the mathematics or chemistry or biology, all are involved collectively to produce, to manufacture, to synthesize the material having desired property. That is a big challenge. In every industry in this world, whether it is an electronic industry or a photovoltaic industry or pharmaceutical industry or food industry, various food materials are being manufactured only based on the material aspects. So most of the essential industries, they look forward the material scientists with a basic background of physics, chemistry, or any field of science involved. So by this way, the Department of Physics of P.K.R. Arts and Science is organizing a wonderful conference, that too with online, with a huge number of participants and with well-known speakers in this potential area, advanced functional materials. So this conference gains importance in this aspect. I know Dr. Radhika, who involved in it. In fact, she was keen in organizing the conference just before the pandemic situation in the month of February or March. She was troubled really but it was not worked out at the time. After 6-7 months,
Host, please unmute the speaker's audio.
Sir, your audio is
Audio.
muted, sir.
oh yes.
Sir, your audio is muted.
Is it okay, madam, now?
Yes, now it's okay. You can go ahead.
So this is the right time that the institution is organizing this event on material aspects, and hope at the end of the day, all the participants will go with so much of knowledge on materials. And this country or this world really looking forward several of the material scientists in the days to come to overcome several problems. Because whenever we are looking for some growth or development in any of the fields of science and technology, one way or other, we need to augment newer materials. Why we are looking for specific materials? Because these materials have very specific properties. So when you can able to tune the properties of a material through the synthesis process, then you can get more efficiency of the devices being fabricated out of the material. So the material tuning through the fabrication is very, very important. For example, to fabricate a highly efficient solar cells, we need a single crystal silicon. It requires a very high pure silicon material. Once again, the crystal growth by Chakralski method. So once again, it's a very important method, cost involved. So the cell will be cost more, but for which people looking for the alternative materials like polycrystalline materials. Method wise simple, so low cost. So naturally the efficiency will also be low. So by this way, you can augment materials and you can tune their properties only through the synthesis or fabrication or growth process. So in this juncture, with these few words as an introductory, I would like to now move to my lecture. Is it audible to everyone? Is it visible?
Yes, sir. It is
Yes, sir.
visible.
Yes, sir.
Yes, sir. It is visible.
Yes. So I'm going to talk on the topic, the crystal engineering of pharmaceutical materials. Well, there are n number of crystalline materials. We use them for our several of the applications. One of the class of materials are the pharmaceutical materials. They have a very peculiar problem that is known as polymorphism. every drug or pharmaceutical material encounter the polymorphism problem. So this can be overcome only through the synthesis or the crystallization process. So this is my outline, the talk today. I'm going to give an overview of crystallization process and different methods of crystallization. And their internal structure, why we are looking for crystalline materials. Just because of their very periodic internal structure, as well as their external morphology. And then their important properties, like directional dependent properties. They're known as anisotropic properties. Only these anisotropic properties gives a lot of importance for the crystalline materials. And then the application of crystals in various fields. And right from the beginning of the crystal growth process, the nucleation of a first solid phase from the parent phase, like from a solution or vapor from melt. And then the mechanism involved into the growth process. With an example, I'm going to focus on solution growth today, growth from solutions, because most of the pharmaceutical materials being grown by solution crystallization. And then I will come to the problem, polymorphism. The same chemical entity will crystallize in different crystal structures at different conditions. Just because of this reason, different polymorphs of a material being obtained, these polymorphs will behave differently. That's why we are looking for a specific polymorph, specific structure, because these are all structure property relationships. And also the stability of the polymorphs play a crucial role here. I will come to it a little later. And then how to control this polymorphism. It is really a problem in pharmaceutical industry. With an example, paracetamol, the material we are using abundantly for our day-to-day use. Right from the laboratory scale and then to some extent the industrial crystallization aspect. Of course, I begin from the very basic concept, just for the sake of beginners. And in this world, every material belongs to one of these three phases, matter, either solid or liquids or gases. Whatever may be the form of matter, but all these built with basic constituents, either atoms or molecules or ions. These are all the basic constituents of this matter. So every matter has its own merits, and we are going to look deep into the solid class, where the solids can further be classified into two different categories. One is crystalline, within which the fundamental units, either atoms or molecules or ions, are stacked in a very regular manner. There will be a periodicity, there will be a regularity, there will be a linearity in the stacking of the fundamental units in all the three-dimensional fashions in a crystal. Whereas in the other form of solid, there won't be any regularity, irregular arrangement of the constant molecules. Of course, materials of both categories are being used in many of the science and applications, science and technological applications. But whereas the crystalline materials behave very efficiently because of their very regular periodic internal structure. Because the properties which we are going to study on them are very much directional dependent properties. So for which you need to measure the direction, you need to apply an external field on the materials along particular direction, and you need to measure the outcome along particular direction, and this material will behave and will show maximum efficiency only along particular direction. So you can tune the property for maximum efficiency while tuning the direction within the crystal. And also you can add whatever atoms or ions externally, from external to internal lattices. You can change the property, you can modify the property, like dopants into the material. By this way, you can increase the efficiency for needy applications. So one can conveniently define a crystal. A crystal is a solid material whose constituent atoms or molecules or ions are arranged in an orderly repeating pattern, extending in all the three spatial dimensions. See, this is a model structure of the sodium chloride, our table salt. It's a cubic crystal system. See, the sodium and chlorine atoms are periodically arranged, very regularly arranged. Of course, when you look into the external morphology, it will be a little different, but there is a correlation between morphology. For our applications, we need to look into the external morphology as well. A crystal here, shown here, is a quartz crystal. It's a naturally grown crystal. This quartz crystal used to grow, underneath the rock, popularly known as rock crystals. It's a very good piezoelectric material. Almost all your wristwatches contains one of the quartz crystal. See, even though it is grown naturally, and their faces are very perfect. So there is a symmetrical arrangement of the external morphology as well as the internal units. So everywhere perfect. From one end to another end, there is a perfection. And there is a definite direction, definite faces. So you can measure all these properties with respect to a single unit, with respect to different phases, with respect to different directions. So all possible only with the crystalline materials. Of course, crystals not only fascinated mankind recently, right from the caveman's age. So thousands and thousands of snowflakes and minerals deposited underneath the earth, and jewels, all the gemstones, natural gemstones, the Navaratnangal, all are single crystalline materials. They grow by nature, naturally grown crystals. Of course, gemstones have fascinated mankind since the times of cavemen and still captivate us. We learn, of course, the real crystal growth science only from the nature, naturally grown crystals. And only last few decades and about 50 to 60, 70 years only, the crystals have fascinated the engineers and scientists, and they become the key materials for modern electronics, optoelectronics, and various technical fields of application. So the formation of crystals in nature, like snowflakes or minerals, this is a snowflake, it has its own symmetry. It is known as dendritic growth. When you pick one or two small ice pieces from a refrigerator and see under the microscope, you can able to see thousands and thousands of structures of this kind, very symmetric structures. And these are all some of the naturally grown mineral crystals underneath the earth. And either in these patients are some of the industrially grown crystals. See, these are all some of the industrially grown gem crystals. And this one grown from our own laboratory, the potassium acid thalode. It is used for electro-optic applications. Because the naturally available crystals are insufficient to meet our modern needs. We need large in quantity as well as quality. So one way or other, we need to necessarily grow these materials, hundreds and hundreds of crystals in industries. So we need to do research from laboratory scale. It has to be scaled up to the industrial scale. And then the desired crystals with the desired morphology, with the desired properties, one can able to augment, one can able to grow with the day-to-day facilities available. See, as far as this small crystal is concerned, this is a seed. It was carefully inserted into the saturated solution, and by adjusting various parameters like temperature, concentration, etc., it has grown up to this larger morphology. These are all natural morphologies. All faces have its own identification, its own characteristic features. So you can select different directions of the crystal plates for your applications. Because most of the applications associated with this material is an anisotropic in nature, directional dependent properties. So accordingly, one can classify the crystals available into two different categories. One is naturally available crystals. Another one is artificially grown crystals, either in the laboratory or in the industry. Under this natural category, snow crystals, minerals, rock crystals, gem crystals, body crystals. Our own body has n number of crystals, like urinary stones, cholesterol, and several bone forms, they are all in crystalline form only. And various proteins within our body, they are all in crystalline state only. And artificially, crystals are grown for various scientific applications, industrially grown crystals, and synthetic gemstones, etc. These are all some of the mineral crystals, and these are all some of the gem crystals. The base material is aluminum oxide grown from industry. So all our gold ornaments, contain several of the gem crystals being grown and cut and polished for their glittering nature. Okay, what is crystallization? So crystallization is the process where a solid forms, a crystalline solid forms, where the atoms or molecules or ions are highly organized in a structure known as crystal. Some of the ways which crystals form are through precipitating from a solution, or a molten state of a solution, high temperature solution, or more rarely deposition that occurs from vapor state, gaseous state. So crystallization is also a chemical solid to liquid separation technique in which mass transfer of a solute from the liquid solution to a pure solid crystalline, that phase occurs. There is a phase transformation. Generally, we need equipments. One of the general equipment is a crystallizer. It's being employed for the growth of any of the crystals. In chemical engineering, crystallization is referred to a term precipitation. Although the result is not amorphous or disordered, precipitation is a common word for various other materials, but for crystals, their crystallization or crystal growth is a terminology. Of course, here there is an involvement of phase transformation. As I said earlier, the matter exists three forms: solid, liquid, gas, or nowadays one more state, the fourth state of matter, plasma. So here there are processes involved in between. So you can freeze a liquid to get a solid, or you can melt a liquid to get melt a solid to get a liquid. By this way, you can vaporize your water to get water gas, and when you condense it, you will get again the liquid. And similarly, gas to solid, some sublimation. You can sublime a solid to get a gas, and by adjusting the temperature, you can deposit the gas from the vapor state to a solid again. So these are all reversible processes for certain materials are concerned. It's a very common terminology. Of course, there is a thermodynamic condition here, involvement of enthalpy of the system. But one can generally define a crystal growth process as a phase transformation either from a liquid state to solid crystalline state, or gaseous to solid crystalline state, or non-crystalline solid state to crystalline solid state. And several of the metal crystals from their non-crystalline raw materials be grown as single crystals. Accordingly, there are several classifications depending upon the materials, whether they belong to inorganic category or organic category, and depending upon their temperature, their vapor pressure, physical, chemical, and other properties, molecular aspects. So based on their various properties, the crystal growth methodology also will differ. So here one can generally classify into four different categories from solution growth, melt growth, vapor growth, and solid state growth. Under the solution growth, there are methods from low temperature solution and high temperature solutions. Under high temperature solution, again, there are methods like flux growth and hydrothermal. Under this low temperature category, there are gel growth and growth methodologies like slow evaporation, cooling, subcooling, etc. Under this melt growth, there are different methodologies introduced by various scientists like Bridgman, Czochralski, P.K.R, Verneuil, etc. The gem crystals are being grown by Verneuil technique, very high temperature zirconia by P.K.R, and semiconducting crystals like gallium arsenide, indium phosphide, silicon are being grown by Czochralski, and various organic materials are by Bridgman. From vapor, there are physical vapor transport and chemical vapor transport, etc. Of course, we used to encounter the word single crystal. What is it? In a crystalline material, for example, this sodium chloride crystal, of course, this is a structure. You can see here, the sodium and chlorine are periodically arranged in the lattices. So every direction has value and distances within the structure has value. So very periodic arrangement. So when from one end to another end, the periodicity extends means for the entire bowl of the crystal means it is known as single crystals. Otherwise, there are polycrystalline materials. The orderly nature will differ from different regions, different sectors, and amorphous, nothing will be there. So this is the best example for a periodicity. Of course, coming to the internal structure, so you can stack the molecules depending upon the chemical nature of the molecules, and you can stack. And these are all some of the best examples for the internal structure of the crystals. This is sodium chloride, one, zinc, cubic, ZNS, and the fluoride categories, and rutile categories, and the provides kit of calcium titanium oxide. This internal structure is very, very important. So nowadays, with the available technologies like powder X-ray diffraction or single crystal X-ray diffraction, one can able to study very clearly the internal structure of the crystals. When you look into the internal structure, there will be a periodic arrangement. When you connect all of them, you can end up with the crystal lattices, an array of points in space so arranged that each point has identical surroundings. And you can identify a small area, the best possible small area, it's known as unit cell, which has very definite directions, 3 axes, and the angles between them. There are 6 parameters, length of axis A, B, and C, as well as the different angles between these axes. So the 6 parameters are going to be the definition of a particular unit cell of a crystal system. So with which one can able to study the complete structural nature of the materials. See here, this is a very simple water molecule. It has a definite bond length as well as bond angle. When they are stacked in lattices, look like this. And from different directions, you can view these symmetrical arrangements, periodical arrangements. So all are very, very important knowledge as far as the crystals are concerned. Here, look here, this is a diamond lattice. So diamond unit cell. This is one small unit cell. Of course, it's made up of only carbon. Okay. And when these 4 unit cells and another 4 unit cells, when they are stacked, you can end up with a small cube of this kind. And again, when you extend by stacking the unit cells one by one, you can end up with a large dimensional diamond. Because of its very rigid stacking, the material will show very high hardness value, mechanically very strong. Diamond is the hardest material in this world. Its hardness number, the Mohs scale is very high. So likewise, you can visualize this unit cell in different directions, and you can study the structural property. All are possible by the modern diffraction equipments. And this is one organic crystal, paramethyl hydroxybenzoate. So you can just see one unit cell here. It has symmetric units. Of course, there are 8 molecular units within the unit cell. These are all known as molecular crystals. Previously, the diamond crystal was stacked by atom, the carbon, in a carbon lattices. Whereas here, it's a molecule by molecule. So every molecule is a unit here, and there are 12 molecular units within the unit cell. And these type of unit cell or the crystal are known as molecular crystals. Most of the organic crystals are molecular crystals. And see here, there are 7 crystal systems. All the crystals, one way or other, they belong to one of the 7 crystal systems. Under each system, there are Bravais lattices. Under the cube, there are 3 lattice types. So 3 different unit cells here: simple cubic, body centered, and face centered. Similarly, under the tetragonal, there are 2, monoclinic 2, orthorhombic, there are 4, and rhombohedral, hexagonal, triclinic, each one. So under 7 crystal system, there are 14 type of Bravais lattices. And with this lattice construction, one has to look into one more step further to look into the symmetry of the arrangements of these fundamental units. You know the symmetry, it is defined here. These are very much symmetrical, and you rotate this object along this axis with a particular angle, you will end up with again the same kind of structure, whereas it not be possible with this asymmetric one. So you can see, visualize the symmetries about a point, it's known as point symmetry, about a line, axis symmetry, or about a plane symmetry. And similarly, with these 3 symmetry elements, and you can do the operations like reflection, rotation, inversion, etc. So these are all the symmetries, and symmetry operations are very much necessary to classify the crystals and to study their structural properties. So there are 32 such combinations of the symmetry elements possible, and they are known as 32 point groups under the 7 crystal systems. In addition to that, even within the crystal, as I said earlier, there are definite directions. This is a simple cubic unit cell. You can able to see this 100 plane. You can identify this plane and 100 direction. Similarly, there are opposite directions, various internal directions and the planes. The plane is nothing but the crystal plane, which is perpendicular to the direction it is projected. This 1 on 1s, 1 on 0s, 102, etc., etc. So all these planes and directions are identified by Miller indices systems. One can very clearly distinguish the directions or identify the directions and the planes of a crystal system right from the unit cell information. So all these information are very, very essential to study the property of the material and for their effective utilization for various applications. Similarly, one need to look into the external morphology as well. External morphology also very, very important. So consider here this is a sucrose crystal belongs to monoclinic system, whereas it consists of this many number of phases. This is a copper sulfate, calcite, and ammonium sulfate, sodium thiosulfate. The sodium chloride, see here, this many phases. Have you ever seen on a piece of table salt with this many phases? When you look under the microscope, you can able to identify all these phases. All these phases have, their own significance. When you measure a property along one particular direction, one particular plane, that will vary with respect to other plane. And also, the crystals could grow along different directions with different velocities. That's why it ends up with different kinds of morphologies. The fast growing phase will have more morphological significance. Sorry, fast growing phase will lose its morphological significance. The slow growing phase will exist in a large morphological importance. So by this way, there is an anisotropy in the growth velocity of the single crystals along different crystallographic directions as well. That's why we end up with different morphologies. These morphologies are very, very important for several of the smaller size crystalline materials. For example, for some medical applications, pharmaceutical applications, we may need spherical type of particles. We may need needle type of particles. So there, you need to adjust the growth along particular orientation. You need to arrest the growth along particular direction. So you can change the morphology by modifying the growth conditions, by adding specific additives, etc. By controlling the growth velocities along different directions, you can change the morphology as per your requirement. It is very, very essential. For example, the material alpha lactose monohydrate we used for inhaler purposes, where it requires only very fine needle-like morphology. But generally it won't grow like this. So you have to do some modification. Accordingly, end up with needle-like crystals, which would be highly useful and preferable. So there you need a real science and technological process of crystallization. Of course, there are several anisotropic properties associated with various crystals. The thermal conductivity, you might have studied, nothing but the flow of heat produced by a temperature gradient, and dielectric susceptibility, it's a polarization along a particular direction by the application of electric field. Piezoelectricity, polarization produced by mechanical stress. In pyroelectricity, most of the IR detectors, we use CCTV cameras and arrays nowadays, all are having the pyroelectricity properties. So polarization is generated along a particular direction when the heat energy is applied along particular crystal plane. The elasticity caused, deformation caused by mechanical stress, and electro-optic effect, photoelastic effect. Here the birefringence, the photoacoustic effect, these are all birefringence created. That means we induce the refractive indices along particular direction by the application of external electric field or external mechanical stress or acoustic signal, etc., etc. So you can easily understand in which direction I'm going to apply the electric field or mechanical strength or acoustic signal, and this will cause some effect along another direction. So there the birefringence will be created. So I can make use of this change in the birefringence for my applications. So this is known as the property tuning through crystal growth tuning. Of course, there are a number of applications. A number of industries, they depend on single crystals. Electronic industry, photonic industry, photovoltaic industry, the LEDs, the photovoltaic, photonic, and fiber optic communications. For fiber optic communication, we need lasers. And one end of the laser, the signal, what we are talking, either audio or video, it will be superimposed to the laser carrier wave through the electro-optic materials, single crystals. In one direction, the carrier wave will be allowed to pass, and the other crystal directions, you can apply these signals, either audio or video, and it will be carried from one continent to another continent underneath, this sea. And at the other end, again, there will be an electro-optic crystal sitting. It will deviate, it will separate the signal from the carrier wave, and further amplification done by electronic equipments, and it will reach your device. So like this, various chemical industries, pharmaceutical industries, biotech industries, jewelry and watch industries, all are looking for single crystals or working on single crystals. These are all some of the basic scientific research fields: solid state physics, materials chemistry, X-ray crystallography. Of course, it's a very core field to study its internal structure connected with the external properties, and mineralogy, etc., etc. There are several types of crystals one can study, and various devices being fabricated. Second harmonic generation from the non-linear optical crystals, and these are all some of the strategically and technologically important crystals. You know, every developed nation have their own well-versed technologies for growing these single crystals. Almost all the developed nations, they have well-established technologies of some of the strategically important materials, and so they are developed nations just because of one of this. This is going to be one of the main reasons for it. For example, to fabricate a microprocessor chip, what we use in our computers, modern devices, electronic cartridges, you know, it needs 9N purity of a silicon. That means 9.9999999. That much of purity is very, very essential in the raw material itself for this kind of electronic device fabrications, microprocessor fabrications. So the Chakralsky pulling technique is being employed for that one. So such a very precise technique with very high pure materials, one has to grow these materials, the single crystals. That's why it is so costly. Okay, coming to the solution growth technique, just I would like to give a glimpse of knowledge on this. How do you grow crystals from solutions? So one of the very fundamental, very simple and elegant technique, but several of the technologically important materials, especially the pharmaceutical materials, biological materials, are being grown by this solution growth technique. It's a very old technique, but still it is a viable technique. Even meter by meter, non-linear optical single crystals are being grown by this technique, this potassium dihydrogen phosphate, for laser fusion applications. You know the solution, it contains solvent and solute. A definite amount of solute dissolved in a definite volume of solvent, and you will get the solution. So there will be an equilibrium attained between the solute concentration and the solvent. But it is a temperature dependent parameter. Increase the temperature, the solubility, the amount of solvent, amount of solute can able to dissolve completely in a known amount of solvent in a particular temperature is known as solubility. It's a very important basic parameter. This solubility is a temperature dependent parameter. When you increase the temperature, the solubility will also increase. But along this line, it is known as a solubility line. It is nothing but an equilibrium line. Throughout this line, there is an equilibrium attained between the solute and the solvent. Of course, underneath this region, it's an undersaturated region. About the region is a supersaturated region. So one can easily understand the situation. Let me give a very simple example. You have a room in which there are 100 chairs, and you are inviting participants to sit in each chairs. So 10, 20, 30, 40, 50. So about 100 participants can comfortably sit in all the 100 chairs. Suppose there are 95 participants only, and 5 chairs are kept empty, means that solution is still in the undersaturated condition. It refers to an undersaturated condition. It needs some more solute molecule to dissolve to attain an equilibrium. When there are 100 participants occupied all the 100 seats, there is an equilibrium between the chairs and the participants. This situation refers the equilibrium condition along this line. Suppose someone is pushing another 5 participants into the room. Already the 100 participants, the 100 chairs are filled, and now there are 5 more participants into the room, but they don't have any chairs. So they have to stand till there are a possibility comes into picture. So there are more number of participants here than the chairs available. So that means for a definite solvent volume, you can only accommodate definite amount of solute into the system. That refers an equilibrium. If there are excess solute presence in the system, means there are 5 more participants into the room, means it refers to a supersaturated system. So for any crystal growth conditions, for any crystal growth process, or to initiate a crystal growth from such a saturated solution, saturated solution means the equilibrium solution. It refers an equilibrium state. To make a crystal growth, to initiate a crystal growth into the system, you have to deviate the system from the equilibrium to a non-equilibrium system. That means an extra concentration has to be necessarily generated within the system, has to be necessarily produced within the system. So that is known as making the solution supersaturated. How it could be done? So that is the methodology here. So creation of the supersaturation, that means excess concentration, is a process of inducing a crystal growth into a solution. So this is the solubility curve. Of course, under this solubility curve, the solution system is in an undersaturated condition. There won't be any crystal growth in this region, not at all possible. So only in the supersaturated region, you can able to induce crystal growth. When you going on increasing the concentration, going on pushing the participants into the room more and more, more and more. At one stage, now the people standing, without chairs, they will accumulate here and there and form a group or something like that. So likewise, you can just, it's a very similar situation here. When you're going on pushing the solute molecule into the system and making the system supersaturated more and more, at one stage, there will be a cluster of molecules. There will be a cluster of molecules. It has a definite shape. And when you're going on increasing the concentration into the solution, the cluster growth will, the radius of the cluster growth will increase further and further. And one stage, it will reach, it will attain a critical radius. till it reaches the critical size of the cluster, there are chances of disintegration of the cluster of molecules as well. So both 50-50 disintegration and integration possible before attaining the critical radius of the nucleation cluster. But once it is achieved, there is no chance for disintegration further. So only chance for further growths. So this stage, the cluster that attains the critical radius, is known as the nucleus, the first nucleus or the first solid particle that has just grown out from solution phase. So this process is known as nucleation. After that, the nucleus will grow into larger size, into macroscopic crystals with a definite morphology, with a definite internal structure. So how do you grow? How do you create supersaturation into the system? So there are three possible ways: in a laboratory scale or industrial scale. Suppose consider this one is an equilibrium state, that is a solubility line. Now you can attain this concentration increasement either by reducing the temperature. Okay, when you reduce the temperature, that means you are saturating the solution at 50 degree. At 50 degree, there is an equilibrium between the solvent and solute. But by reducing the temperature to 49, so we have an excess concentration than that of the saturation or equilibrium at 49 degrees centigrade. So this is known as supersaturation here. It is a measure. Okay. So likewise, when you reduce the temperature from the saturation point, you establish excess concentration into the system till attaining the critical radius. The other way, by keeping the temperature constant, by allowing the solvent molecule to evaporate. For example, you have 100 chairs, you have 100 participants sitting on them, but you are taking away 5 chairs from the room. So now there are only 95 chairs within the room, but 5 more participants, they are standing without a chair. So now also the excess concentration is generated. So by this way, you can allow the solvent molecule to evaporate and you can increase the concentration available to this level. And this line AC refers the both by solvent evaporation or temperature reduction. The first one is known as slow cooling, and the second one is known as slow evaporation. And this middle line refers both. So either way, you can achieve the excess concentration to this level. So this dotted line is a boundary between two different levels, supersaturation levels available within the supersaturation region. The first one is a metastable region where there is no possibility for a nucleation because the radius of the cluster will not attain the critical size. It will attain only along this dotted line. Once it is attained, further growth will take place. But whereas the supersaturation level above this region known as Labelle region, so a scientist who invented this one, there are n number of possibilities for the nucleations of solid particles within this. See, it's uncontrollable manner. You cannot able to control the number of nucleations in this region because of excessive supersaturation. Whereas in this region, you won't get any nucleation, but you can grow bulk single crystals by placing a proper seed within this one. Seed means a portion of the crystal cut from the already grown single crystal. When you place a seed here, the surface of the seed will grow using the excessive concentration available in this region. It is known as metastable region. So several of the bulk single crystals, strategically important bulk single crystals, are being grown in this region. And for various industrial purposes, with the multi-nucleations, one can select this one. So all depends on the supersaturation created within the system. And of course, this slide explains how the generated growth unit moves into the surface of the crystal and slowly. So all these, these boundary conditions can be able to adjust by adjusting various crystal growth parameters. So from vapor phase, from liquid phase, this is a growing crystal, constructed crystal already. This is a solution environment. This is a boundary. Here there are a diffusion process that will always take place. So the solute molecules will attach into the system in a two-dimensional nucleation basis, and the solvent molecule will escape from this boundary. Of course, nowadays there are techniques available with which one can able to see the mechanism behind any crystal growth process. So this mechanism is known as screw dislocation mechanism. In a crystal, the screw dislocation helps to grow single crystals along particular direction. You know the dislocations, edge dislocation, screw dislocation, etc., possible in a single crystal. So if there is a screw dislocation, the Berger vector and the dislocation directions, they play a major role here. See, here there is a smaller size nucleation, the cluster of molecules. It is known as two-dimensional nucleation. This particular layer will grow. So this will rotate something like this, like moving on a staircase. So every step will be completed by the addition of growth units, and this step will propagate, and likewise a small area, it's expansion. Finally, the particular crystal surface will grow continuously, but you have to maintain the condition accordingly to continue the growth uniformly throughout the growth period. That is a big challenge associated with any crystal growth process. Otherwise, you will get spurious nucleations, non-controllable nucleations on the surface of the growing crystal that will spoil the single crystalline nature of the material. That will induce more defects into the crystals. When there is a defect, definitely that defect will affect the perfection of the crystal and also the property of the crystal, and finally the efficiency of the devices fabricated out of the crystal. So crystal growth process is very, very important and dedicated process. More than a science, it is an artistic processes. Okay, coming to the main business, the pharmaceutical materials, which encounters always the problem of polymorphism, and how we are going to manage these polymorphic problems, and how you are going to grow the desired polymorphs of a particular pharmaceutical material through solution crystallization. Of course, here is a definition for polymorphism. The phenomena of a chemical species having more than one possible crystal structure. The same chemical entity, same chemical formula will crystallize in different crystal structure. One in cubic, another one is monoclinic, another one is orthorhombic at different conditions. So every crystalline structure will show different properties. And these are all known as polymorphs of the material. And these polymorphs may have different stability at room temperature environments. Some will be more stable throughout the environmental conditions. Some of them are very less stable. They will stay only for few hours or few seconds or few weeks or few months in that stage, and then they will disappear. If the medium is suitable for them, it will transform from one form to another form. So there are stable forms and there are highly unstable forms. In between, there are metastable forms also. So accordingly, these metastable forms will transform into either unstable or a stable form after a period of time. Or sometimes this stable form also will transform into some other metastable or unstable forms when they are subjected to external forces, external fields, like by applying thermal energy, by applying some electric field, magnetic field, pressure, etc., etc. So this polymorphism is not only relevant to pharmaceuticals and also relevant to various agrochemicals, pigments, dyestuffs, food materials, explosives, etc., etc. So one best example here is the carbon. The carbon is a very simple element. It's a constituent for both diamond, graphite, and nowadays the graphene, the two-dimensional sheet. So all the three are here at least considered two, diamond and graphite. Both are made up of only with carbon. Carbon is the basic constituent. But they are different crystal systems. The diamond belongs to cubic system. I think I had shown some of the pictures. Diamond unit cell, very rigid and very hard, hardest material in the world. This is a lattice distance and it's a covalent tetragonal binding. Very poor conductor. Thermally, electrically, very, very poor conductor. Whereas the graphite, once again, it's a constant of carbon only, but it belongs to hexagonal crystal system, rather very soft material and having layered structures of this kind, something like this, and very good conductor. So different characteristics between the two different structures. One is very hard, another one is very soft. One is highly conductive, another one is non-conductive. So two different extreme properties from the same chemical entity. That is the beauty behind the polymorphism. And coming to the pharmaceutical materials, very often they change from one form to another form. Of course, when you look into the historical events of polymorphism, first it was invented in 1820s itself in arsenic salts. It is basically an inorganic substance. It showed three colorations. One time it is a metallic gray at room temperatures. When you cool it to rapidly to a Lower temperatures, it becomes yellow and becomes black at very high temperatures. So with the temperature, it changes from one color to another color. This is just because of changes from one crystal system to another system. This was first recognized with arsenate in 1820s itself. Later on in 1832, scientists P.K.R. and colleague Lebeck discovered the first phenomenon of polymorphism and explained in a more scientific way with the material benzamide. Benzamide crystallizes into two different crystal structures. One is a needle type axial morphology, another one is columnar type, the rhombic crystals. The silky needle slowly replaced by the rhombic crystals. They switch over from one to other. It was recorded in 1832. Later on, there are a number of materials. Even the history has its own impression because of this polymorphism. You know the Napoleon Bonaparte, a French political leader who sent an army to defeat with the Russian army in 1812 with highly decorated uniforms. The soldiers, the buttons and the coats, they're made up of tin. Initially it was, like this, white metallic tin. So after a period, because the Russian temperature at Moscow was, at sub-zero, just because of very cooling environment, this metallic, white metallic tin is transformed into the other form of alpha tin. It becomes gray in color. The soldiers believed that it is the wrath of God. So their morale became so low that they faced a pathetic defeat at the gates of Moscow just because of this polymorphism. And the scientific reason for this crumpling of the buttons is very, very interesting. At sub-zero temperatures of Moscow, the metallic white tin underwent a polymorphic transition to the stable but the non-metallic gray tin, thus reducing the decorum of the mighty soldiers. So that was a belief in those days without much scientific knowledge, but now the world realizes the problem of polymorphism, especially in pharmaceutical industry. But even in recent times, there were several problems being encountered by polymorphism by these pharmaceutical industries. So you must be knowing this, familiar with the name ritonavir, the first drug discovered for HIV. The molecule was designed and believed that it is going to be a remedy for HIV. The industry known as Abbott, the pharmaceutical industry, when they first examined, it belongs to one particular crystal structure and form and passed all the tests initially. The company manufactured in a large quantities because for the want of, the huge market. And after the mass production, at the final stage of the quality control, during the quality control, that material failed one of the important tests. It is known as dissolution test. It didn't dissolve. The solubility get reduced. The solubility is a very important parameter for any of the drug material because the material has to be dissolved within a particular time in our body fluid, then it has to react. It failed the test because of the influence of another form. That means the form 1 initially invented, after a period of manufacturing, transformed into form 2. So the presence of form 2 polymorph of this retinover disturbs the or reduce the solubility of the form 1. So that was a problem. So there is a great loss for the industry as well. So one has to be very, very careful in selecting the desired polymorphs having desired properties. And one more thing, one has to preserve the drug materials in a particular environment. That's why the expiry date behind any of the drug materials are very, very, very important. And also the environment has to be highly protected. So this was the first, failure by the industry, then they recovered. And what do you mean polymorphism? How it occurs in crystalline materials? Coming to this example, paracetamol, there are different kinds of packing of the molecules. So there are conformation of molecules. These are all molecular conformations. But these conformers packed in two different ways. So this is belongs to the monoclinic system, whereas in the other form, it is packed in a very different way. So this is also possible, the orthorhombic. But this one is more stable at room temperature. This one is a metastable one. This is known as packing polymorphism or arrangement polymorphism. The difference is in the packing of the conformation of the molecules. Another type of polymorphism is known as the conformational polymorphism. So in the conformation itself, there will be a change. Now, this is a boat-like cyprone molecule, and the molecule itself will bend something like this and form another lattices. But both belongs to same crystal system, but with different unit cell characteristics. So this is one type of lattices, and this will form another type of lattices. These two have different characteristics, even though they both belong to the same crystal system, sometimes same space group also, but with different lattice parameters, with very minute changes within the molecular range. That will give some effect on the property. One form will be stable and another one will be metastable, etc., etc. And another kind of polymorphism where the material vanillin, it's one of the food material, where the form 1 and form 2, one is looks like a columnar, another one is like a needle, both will appear at the same crystal growth conditions. That is the problem. So one has to very carefully imply the parameters to select the nucleations of the desired polymorph. That is the challenge here. This is one kind of stacking and another kind of stacking. So only the small change. One is orthorhombic, another one is monoclinic. Sometimes these lattices will
Sir, we are not able to hear you, sir.
Is it okay, madam?
Yes, sir. Yes, sir.
Oh, okay.
Thank you, sir.
Okay, so just because of this incorporation of some solvent molecules into the lattices, the structure will become different nature and will show different properties, but looks like a different polymorphs. But in reality, they are not polymorphs. They are looking like polymorphs. They are known as pseudopolymorph. And when the solvent molecules are incorporated, they are classified as solvates. And when the water is used as a solvent there, they are known as hydrates. Accordingly, according to different structural parameters of various polymorphs, the properties also get changed. What are the properties? The packing properties, the molecular volume or density. So one way or other, we have to pack the molecule into tablets, and their refractive index, conductivity, both electrical and thermal, the hydrophobicity, and various thermodynamic properties like melting and sublimation, temperatures, internal energy, enthalpy, spectroscopic properties, and kinetic properties like dissolution rate, solid-state reaction, stability, etc. Surface properties, and mechanical properties, hardness, tensile strength, etc. etc. So coming to the thermodynamic characteristics of the polymorphs, there are two different classifications. One is monotrophic system, another one is enantiotrophic system. Where in the first case, the diamond and graphite, there is no reversible transformation is possible here. Whereas in the enantiotrophic system, so like water into ice and ice become solid, again water. So this is a thermodynamical environment. At one particular point, you can change from one phase to another phase easily. So why we need to study the polymorphism? So depending upon their relative stability, one of the several polymorphic form will be physically more stable than the others. Stable polymorph reference represents the lowest energy state, whereas the highest melting point and least aqueous solubility. Whereas the metastable form, which has a higher energy and lower melting point, high aqueous solubility. So likewise, the metastable form converted to stable. Madam, hello.
Yes, sir. Yes,
Yes.
sir.
So the metastable form shows better bioavailability and therefore preferred in several of the formulations. So about 50% of the pharmaceutical materials exhibits polymorphism, in which only 10% are present in their metastable form. It influences various fields, not only pharmaceuticals, food materials. The chocolate, it has 5 different polymorphic forms. When you change the temperature, the taste and the crispy nature will be lost. So the industry is really struggling to provide you the correct chocolate as per your environment. And fight chemical industry, fertilizers, photochemicals, etc. And what are all the impact? So polymorphism is important in the development of pharmaceutical ingredients. So most of the pharmaceutical drugs are polymorphic. It is formulated and marketed in crystalline form only. It has direct medical implications. Drug molecules are highly functionalized and can self-organize in several ways in the solid state with nearly same lattice energies. Statistically, about 85% of active pharmaceutical ingredients exhibit the pseudopolymorphism, and around 50% of APIs have multiple forms. So these are all some of the properties which would affect by polymorphism, solubility, bioavailability, manufacturability, etc., etc. And what are the factors affecting the polymorphism? So once, after completion of the product, either the pharmaceutical product or drug or tablet, what are the other environmental property parameter which will affect the polymorphic stability? The temperature and humidity. The storage conditions are very, very important. At times the humidity also. That's why the tablets are, completely sealed. Sometimes the photostability also. Some drug molecules will sensitive to light. After exposing to the light energy, it will transform to another form. So photolytic degradation will occur. So it is very, very important. So the package has to be properly done accordingly. And various solvents, it is an important one to fix the growth mechanism as well as morphology and kinetics of the crystal growth process, etc. During the process itself, it may change from one form to another form. So accordingly, the industrial processes have to be designed. The grinding is the main process. When you apply some mechanical force, and the drug material will transform from one to another. And surfactant, will affect the polymorphs heavily. And finally, the compression. It is known as the tableting behavior of a particular material. It's known as compaction behavior. So how compact the materials to form a tablet. Some of the lattices will not cooperate for this compaction. So it's very difficult to compact, to bind the molecules. You need extra binding materials or incipient materials. And some will do in a better form. Okay, these are all some of the important things. And after the formation, after the manufacturing, it may change from one form to another form. There is a polymorphic phase transformation. A metastable crystalline form can convert it into a more stable one like this, with a small difference in the stacking. And undissolved form, anhydrous form may become the solvates or hydrous form by absorbing moisture, from the environment. So the preservation is very, very important. And while preparing itself, many of the occasions, even we used to face this problem in our laboratory. One fine morning, we would get some crystalline forms. We'll confirm that it belongs to a particular system, etc. After a period, when we try to repeat the same experiment, we won't get it. That is the difficulty. So the appearance and disappearance of these polymorphs and their stability at the environmental conditions and the experimental conditions, and keeping the experimental procedure in a very, very procedural way, all are very, very important. Otherwise, you will miss some of the desired polymorphs while the preparation itself. So that's why the industries, as soon as they invented a particular process of making a particular pharmaceutical material, immediately they patent it. That's why some of the drug materials, they cost more, very expensive, just because of patterning nature of the industrial procedures. Otherwise, all are simple, fine chemicals only. As a chemical, it won't cost much. But after the processing, at the stage of the medicine and keeping the medicine in desired polymorph, so all, the processing will gain more and more expenses. Okay, there are various processes, methodologies one can adapt, and we used to adapt in our laboratory. So using various crystallization methodologies, the solvent evaporation, and slower set cooling temperature methods, and solvent diffusion methods, and by applying various external parameters, and then sublimation. Okay, here I would like to give an example of the crystallization process of paracetamol and what are the problems we encountered at the laboratory scale, and how do we manage to get different polymorphs of paracetamol from our laboratory, our own experiences. The paracetamol, it's a very familiar molecule, very simple molecule. We used, in every walk of our life as an analgesic or antipyretic drug for common fever and body pain. But it has three forms. It crystallizes in monoclinic form, which is quite stable. What we use, as a paracetamol tablet, they are all, belong to the stable monoclinic form only. But the other form is very, very interesting, metastable form. It belongs to orthorhombic. During our investigation, we could able to find out one more paracetamol. And we reported first time, it's highly unstable. Of course, these are all the three different forms of paracetamol. The monoform crystallizes in the monoclinic crystal structure with the columnar morphology of this kind. These are all microscopic pictures, of course. And whereas this orthorhombic form, they used to crystallize in a needle-shaped crystals. But it is metastable only. It will last only for a few minutes to few days, okay, during our process, depending upon the concentration and temperature. And then it will transform to another form. During the growth process itself, it will change, transform. Solution-mediated polymorphic transformation we used to say. And while investigating these two, and occasionally we used to get this unstable form. It's highly unstable when compared to these two forms. It lasts only for a few seconds. I'll show you some pictures later on. And here is the distinction between form 1 and form 2. Monoclinic form 1, this is a crystal structure like a zigzag arrangement of these two aromatic and acetyl groups. And between the parallel planes formed by the aromatic polar rings, acetyl groups of molecules belonging to the two different planes are interpenetrated, something like this. Here, there is a problem faced by the industries. You cannot force the molecule to compact into a tablet because of this kind of zigzag molecular structure. So you need some incipient to pack these molecules. So then the size becomes large. Whereas in the other case, metastable form, it is something like this parallel planes. Okay, there are no molecules or any chemical groups are interposed between these parallel planes. And these planes are also characterized by high molecular density when compared to this one. So you can easily pack these molecules into a smaller volume, and also you can pack more number of molecules into a smaller molecular volume. So the tablet size, will be typically very, very small, very easy to consume, and the efficiency will also be more. In several ways, this form is very much needed by the industry. But the problem here is one has to struggle to nucleate this form too. It's not a simple task. And after implementing various other techniques, we were successful in crystallizing this one. And some other researchers as well found this one, but it's not stable. It is a metastable one. Of course, these are all the crystallographic differences. Okay. So monoclinic, these are all the crystallographic parameters, orthorhombic. Okay. Right. So how these forms will transform from one to other in a solution medium. After the nucleation, see here both the forms are exist. These monoclinic crystals, and the needles are orthorhombic. See, both exist here together. After 4 minutes, 8 minutes, it's a continuous photography, microscopic photography, in situ observation. See here, both the polymorphs, they do grow in size. Yes, yes. And after 15, 17 minutes, these mono nucleations or crystals continuously growing in size, whereas these orthorhombic needles, they become blunt and they become thinner. So after a period of about 30 minutes, this orthorhombic completely dissolved into the solution, and only the stable monoclinic retains. So that kind of stability, here only 30 minutes. In some other process, when you redo this experiment with the different experimental conditions, this will last for 1 hour, 2 hours, or sometimes 1 day, etc. And this is the appearance and disappearance of the unstable polymorph we encountered. The needle lights are unstables, whereas the smaller columns are monoclinic. Okay. So it's only 8 seconds. This unstable nucleations completely dissolved, while the other monoclinic is continuously growing. So that is the beauty. So one has to carefully design the crystal growth parameters to capture this. This is another solution mediated polymorphic transformation from unstable to mono paracetamol. See here, both polymorphs exist. So only this unstable form exists here. And in between, there are nucleations of the stable monoforms. And these monoforms, continuously growing, while the needle-like unstable polymorph continuously dissolving. So, complete transformation of the unstable to the monostable. Okay. So this is known as solution mediated polymorphic transformation. With the best microscopic facilities available, thus we could be able to capture these photographs very carefully by one of my research scholars, Dr. Subha. So likewise, we need to control various parameters to preserve these desired polymorphs. The temperature or pressure, concentration, solvents, additives, various growth techniques, seeding techniques, and cooling rates, etc. etc. So control is not always easy to achieve or maintain. You have to survive with the material. You have to learn its habit. And crystallization technique is still the nature of art and is challenging. And so we employ different solvents to grow them into bulk. Of course, by anticipating different polymorphs, different kinds of solvents we used. Every solvent has its own effect on the growth. Different polar aprotic solvents and non-polar solvents we used, prepared the solutions and filtered, usual growth process. These are all the list of solvents selected right from the water and the polar nature, dipole moments, evaporation. At room temperature is an evaporation rate, the pH of the solvent and the solution, and these are the solubility and nucleation time, the time taken to get a first speck of solid from the saturated solution after the saturation condition is achieved. These are all the morphological aspects. Of course, one has to investigate the surface chemistry also. For every crystal, every polymorph has different facetings. So every crystal facet has some definite protruding groups of the molecular groups, and these protruding groups will react with different solvents in a different manner. So you have to carefully select the solvents accordingly to control the growth of the polymorphs and their morphology to a particular desired shape. So all this has to be investigated continuously. And another procedure we employed here is a zip cooling technique. We introduced first time in the literature, and parameters we took. One is concentration, another one is temperature, another one is stirring of the solution, its velocity. We adjust the concentration in this range and the temperature in this range, and various steps followed for stirring this solution continuously. And we cool down the solution from a high temperature saturated condition to room temperature or below room temperature conditions. And there we could able to create super saturations in these levels, sigma. So we could able to first time segregate the regions of nucleations of different polymorphs of paracetamol. See, within this supersaturation region, I'm speaking on this relative supersaturation. So we could achieve only the mono nucleation of the paracetamol. Another in between, there are mixed times, both the nucleations appear, whereas another region, only the ortho need. So when you set the conditions for this particular region, you can able to crystallize only the desired polymorph. So this is an outcome of the process. And 3 polymorphs, prismatic, needles, and fiber-like. The morphologists, investigation on the morphology is very, very important to study their application-oriented properties. And then the confirmation is by X-ray diffraction. This is a powder X-ray diffraction of form 1 and form 2. It's a distinction here, and the refined lattice parameters. Okay. So this is an ultimate confirmation of the polymorphs after their growth. And another technique we employed here employing some templates. We wantonly inserted some of the templates of polymers of different types into the solution, because here the nylon 6x6 or polypropylene or PVC, they have different molecular structures, you know. They are non-reactive with respect to this paracetamol solution. But when we introduce, we will be able to nucleate the desired polymer. That was our success here. And of course, this is a solution at normal conditions without any polymer templates. We adjust the relative supersaturation up to this range. We obtained only the mono. There is no orthonucleation rates. Whereas in the presence of some polymer solutions nucleated different polymorph with nucleations at different supersaturation conditions. So here the polymers induced selective nucleations at different crystallization conditions. So monoclinic, only orthorhombic, something like this. Of course, my student did a number of experiments with 3 different polymers, and this is a pure case with the range of supersaturations and concentrations. In pure solution yielded only the monoclinic, whereas the nylon 6,6 like this, mono plus ortho, and PP and PVC, etc. So this region is very, very important to crystallize the form 2. So likewise, one needs a lot of patience and to do n number of experiments with varying parameters to map the crystallization procedures of this material. And these are all some of the outcomes. See here, nylon 6x6 with the time in seconds. See the polymers and the nucleations. See, needle light. And this is in the mono plus ortho. Both nucleations appear here for this particular condition, whereas the sigma is 1.48, where here only ortho conditions, only the needles, they started growing. And the supersaturation is 1.62. So polypropylene, once again the same situation. Okay, and here also. So we were able to segregate the region of nucleations of desired polymorphs. Okay. And PVB also favored very much in getting the desired polymorphs from desired regions. That was the success of the experiment. And these are all some of the nucleated close-up monoclinic crystal. And these are all some of the needles, orthorhombic polymer from nylon and PP. Similarly, the PVC, monoclinic as well as orthorhombic nature, carefully captured under microscope. So ultimate confirmation is once again the powder X-ray diffraction for the monoform nucleated with these polymer templates, and form 2 orthorhombic nucleated by these 3 different polymers. So these are all the structural parameters for form 1 and form 2 compared with the literature value. Okay, very much confirmed here. Another confirmation is the differential scanning calorimetry. So with which one can find out the phase transformation from one form to another form. Whereas the monoform doesn't show any polymorphic phase transformation till it's melting. Whereas the form 2 ortho, since it is a metastable, it shows an endothermic happy well before this melting. So this, after investigation, we found that there is a phase transformation from form 2 to form 1 here. Is yet another confirmation. It's above ambient conditions. Another confirmation for these polymorphs. And then we tried to grow bulk single crystals of paracetamol. They're successful in growing bulk from the monoclinic. Of course, it's a seeded technique. We employed after a month, we could be able to get this one. It's a small seed crystal, after regular monoclinic phase. And this is the periodic growth seed crystal. And this is a growing crystal after 14 days. It's a kind of a stirrer implied. And this is a close-up of the growing crystal with natural faceting here after 23 days. And this is after harvesting. Okay. Okay, it's a time to conclude. So polymorphism has a great impact on the manufacturing of various pharmaceutical products. So crystallization plays a pivotal role in controlling the polymorphism of not only pharmaceutical materials, but various other materials. So the solvents used as a crystallization medium has major impact on the paracetamol crystal morphologies, habits. For the first time, preferred nucleation regions of all the 3 polymorphs of paracetamol are optimized in terms of different supersaturation ranges. During the subcooling crystallization process, we introduced first time in our laboratory solution mediated polymorphic phase transformation from unstable to mono, unstable to stable, metastable to stable, ortho to rhombo polymorph have been studied. The rarely reported nucleation of unstable polymorph of paracetamol has been observed for the first time through in situ observation. They last only for seconds. And the polymer-induced crystallization technique offers a novel and effective way of obtaining stable and metastable paracetamol polymorphs with high purity at various supersaturation ranges. That's all. To summarize, I begin with the crystallization overview and methods of crystallization, their internal structure and external morphology, anisotropic properties of crystals, their application in various fields, nucleation, growth mechanism, and the method of growing single crystals from solutions with some fundamentals to some extent. And then polymorphism, by giving some knowledge on it, and how to control the polymorphism. And then with an example of the crystallization of paracetamol in our laboratory, I tried to explain the polymorphic crystallization process. And these are all some of the good quality single crystals grown from our crystal growth laboratory, Bharathiar University. Some of them are really good in quality and very rare to get. And finally, I acknowledge all my postdoctoral and doctoral students of my group for their contributions towards this piece of work. Thank you, one and all, for your patience for nearly 2 hours. And thanks.
Thank you, sir.
Organizing committee for your for this great
Ma'am.
opportunity. Thank you very
Sir,
much.
thank you so much. And this session is open for any queries or doubts.
No, I just want to thank him, Kana.
Yes, ma'am. Yes, ma'am. Please, ma'am. Please.
Thank you very much, sir. Excellent presentation. I think anybody can do research in crystal, I think now. Sir, are you listening?
Madam. Thank you, madam. Thank you very much indeed. Thank you.
Can you, I don't know whether you can see me. It was an excellent presentation, and even I could follow many of it,
Just a
crystal
moment,
growth
madam.
and
I would like to.
properties, everything. So simple and simple examples you used, and such a lot of patience in explaining. Excellent. A researcher can go ahead and do research in crystal, I think. Such a lot you have given, sir. Thank you. Thank you very much
Thank you very much,
for you.
madam. Thank you very much.
So many charts and so many things you have prepared, slides. And I think you can help our students in crystal growth in your laboratory. I think you have grown lovely crystals also in your lab.
Sure, madam,
Finally,
definitely.
show that also. Thank you, sir. Thank you very much. Just by saying thank you in the form of words, it's not sufficient. We are really indebted to you because you have spent such a lot of time preparing. Maybe you have used your research scholars or students, but still, the presentation and learning it and giving it in detail, it needs so much of time. You have taken trouble. So we are really indebted to you, sir. Thank you. Thank you, sir. Thank you.
Thank you very much, madam, for your comments and for this
Thank you.
opportunity. Thank you. If there are questions, yes.
Students, you can make use of the opportunity and ask him questions, clarifications, so easily available to us.
You can ask any type of questions if you have.
Sir, you spoke about the expiry date of the tablets, and sometimes it is dangerous how it changes its, what is that? That solubility, or I don't know what it is, that the term
Yes.
that you use.
Yes.
So what happens sometimes, this illiterate people and without knowing, even educated people, they take such tablets even after the expiry date. And in some of our pharmaceutical companies, I think it is not even given clearly, the expiry date. So
Yes,
don't you
yes,
think it is, yes, I don't know, like a layman, I'm asking you a question. I don't know how the problem can be solved or what can be done about it. If they consume, to what extent it will affect the health or...
Madam, definitely the effect will be severe.
Yes.
And sometimes, this chemical will behave very differently.
Yes.
And some of the cases, that leads to death also.
Oh.
Yeah, yes, because it will give very drastic effect. In some cases are there really.
Mm-hmm.
And that's why the expiry date is very, very important. So,
but in India, are they
yes.
giving expiry date clearly, sir, on the...
Yes, madam, it is given nowadays. It is
Hmm.
given nowadays as per the direction of our government.
Yes.
It is exclusively mentioned, and it is monitored by also our government system. And it is also our responsibility, our social responsibility. One has to sell only, the medicines, those who have enough expiry date.
Okay.
So we need to also have to be very, very careful.
Careful, yes.
Yes. We have
But
to be very
illiterate
careful.
people,
Yes.
to what extent they can understand this.
That is a problem, madam. That is a problem. And we at least, our educated community should, come forward to help the people. And those who are taking this business, the pharmaceutical business, it is their responsibility as well. So it is some at times it will give very, very strange effects.
Yes.
Yes. That's why these companies are earning a lot, madam, just because of keeping this date.
Yes.
Technology behind it, and
I know.
they patronize everything.
Yes.
That's why some of the medicines, they are really very, very costly.
Sir, is it okay if we buy medicine from Amazon and all? Will it be safe?
Of course, there are some branded companies. They have to follow the very strict norms. There are universally and globally there are certain norms.
Okay.
Have to necessarily follow all the norms.
Yes.
And also in every country there are some very strict norms.
Yes.
So the companies or industries or in the people, those who are involving in the business, have to be necessarily follow all the norms, madam. Only the
Yes.
rules and regulations, really protect us from the chemicals.
Yes. Yes. It was a useful session, sir. Really, I mean, very simple language and down to earth and elaborate preparation you have done. So great, really.
Thank you
Thank
very
you.
much, madam.
Thank you.
Blessings.
Sir, one question is posted in the chat box from Ms. Manasa.
Yes.
She has asked, sir, is there any difference between natural and artificial diamond crystals with respect to crystal structure?
Yes, of course. The naturally available diamond crystals, they are really formed underneath the earth mantle several kilometers down. Because to make a diamond, you need a lot of pressures as well as the temperature. Though the carbon is a very simple element, when the sufficient amount of quantity of carbon minerals available underneath the earth mantle, and with so much of temperature, several thousands degrees, and so much of pressures, then the material forms underneath the earth mantle. Once after this earthquake and all, this formed and grown natural diamonds, they come out, okay, and then they will be there, underneath the rocks, etc. And we need to find out carefully. But by observing their importance, because the diamond is a big industry now, the applications of diamonds also very huge. So right from your drilling of your earth, the bore well drilling, at the end you will find one hammer. There, only the diamond coated metals will be there. And all the cuttings, polishing surfaces have diamond coated things. So since we need a large amount of diamond, so the industry, the diamonds are industrially grown by various industries throughout the globe. And now the technology, due to various technological development, it is possible to grow diamonds of much better quality than the naturally available one. So you can grow the diamond crystals without any contamination of other materials, without the contamination of other elements, etc., etc. And also you can augment this with sophisticated instrumentations nowadays. You can also grow with varieties by doping, and you can introduce different colorations also. But Today, unfortunately, I didn't have the slides on diamonds, but there are number of industrial processing are available for diamond growth. Yeah, yes. Nowadays, the technology has come up to a level we can able to grow equal quality diamond single crystals in
So
far
can you grow it in your lab, in Bardha University lab? Is it possible to grow this diamond
No,
crystal?
madam. No, because it is really, expensive technique.
Very expensive, yes.
Yes, madam. It's an expensive technique.
At
Only
least
the,
experimental thing, is it possible? I was asking.
yes, madam.
Yes.
Of course, it needs one heavy crystal growth puller. It's known as P.K.R plus technique, where it needs huge instrumentation. It's very, very difficult to manage such instrumentation in a laboratory scale, like in a university system. The யானை கட்டி தீனி போடுற மாதிரின்னு வச்சுக்கோங்களேன். So like element feeding, elephant feeding.
Actually, I'm curious to know if you can have maybe industry and institution and industry
Yes.
link.
Yes.
Bardha University can help in the growth of diamond, and industry can make use of that, and they can make such investments. Can you think of such possible events in future?
Yes, madam. Yes, madam. It's a big area, diamond growth, and definitely, if there are some opportunities, we can able to do that. But unfortunately, in this country, this is a problem.
Yes.
Here, this relationship between industry and institution, it's very poor.
I know.
Connected. We are poorly supported by industries. Whereas in the foreign developed countries,
yes,
every industry, they come forward with some problems and they approach the institutions with some problems. They're looking for some solutions with the institutions. There are mutual understanding.
Actually, researches can go on, in the institutions, and that will be useful to the industries. Maybe only then the education becomes fruitful
Sure,
and productive.
definitely. It will be meaningful, madam. It will be
Yes.
meaningful. So, if such binding is established in this country, definitely our country will come up,
Yes.
very soon. Yes.
Thank you, sir.
All
Thank
the
you.
developed nations, they establish such links, madam. That is the main reason for, their capabilities in manufacturing several of the materials of importance of today.
Then we can talk about application of science in the in practical field.
Yes.
See, here when you are learning everything in the lab and theoretically you learn it, and if it is not being used by the industries,
Yes,
and
ma'am.
it becomes just academics.
Yes, ma'am.
And you are all so knowledgeable, and you have done so much of research.
Yes.
And input is there, and there is nobody to make use of it. Really, I feel sorry about it. Thank you, sir. Thank you.
Thank you very
Thank
much,
you.
madam.
I'm going beyond your lecture.
Yes, madam. Thank you. Yes. No problem. No problem.
Radhika, if there are no questions from poor sir, he has spent so much of time with us.
Yes,
He must-
ma'am. Yes, ma'am.
Oh, no issue, madam. I'm happy.
Yes.
We have come to the closure, ma'am. Yes.
Thank you, sir. Thank you so much for the wonderful session. Gratitude is a powerful catalyst for happiness. It's the spark that lights a fire of joy in your soul. Here comes Ms. N. Subhadra Madam, Assistant Professor, Department of Physics, to deliver the vote of thanks.
A pleasant good afternoon to one and all present here. It gives me immense pleasure to deliver the vote of thanks for this session of National Conference on Advanced Functional Materials and Engineering. My sincere thanks to the resource person of this session, Dr. K. Srinivasan, Professor and Head, Department of Physics, Bardha University, Coimbatore, Tamil Nadu, for accepting our invitation and for spending his precious time in educating us on today's topic, crystal engineering and pharmaceutical materials. As explained, the crystallization process, its properties, applications, both mechanisms of the crystals and everything excellently. His explanation on the polymorphism, its control, and polymorphism in paracetamol was indeed interesting. Thank you, sir, for your valuable presentation. Now,
Thank you. Thank you very much. Thank you, one and all, for listening. Thanks for this opportunity. Thank you very much indeed.
Now, I would like to thank our secretary and correspondent, Sri P.N. Venkachalam sir, for encouraging us to arrange such a conference. My heartfelt thanks to our CEO Madam, Professor Jagata Lakshmanan, for her wishes and inspiration. I would like to render my gratitude to our principal, Dr. D. Maithili ma'am, for her moral support and valuable guidance forever. I must mention my deep sense of gratitude to all the faculties, research scholars, and students who have been attending this national conference for their active participation. Once again, I thank you all. Thank you.
Thank you, sir. Thank you.
Thank you very much, madam. Thank you.
Sir, thank you very much, sir. It was very informative. I hope our students and the participants benefited from what you told us. Even we were able to understand, sir. Thank you very much, sir.
Thank you very much, madam. Thanks a lot.
Thank you, sir.
Thank you all. Dear participants, please assemble back by 1:55 p.m. for the afternoon session. Thank you all.